Imagine that you are lying beneath a clear, dark sky. The world around you is quiet. Above you, the stars seem to hang in the darkness, like tiny pinpricks in a vast curtain of night. Some of those stars are young, and some are old. Some are calm and steady, and some are waiting to die in the most powerful way the universe knows. They're waiting to become supernovas. Tonight, we are going to drift slowly into the story of those stars. We won't rush. We'll move gently the way your thoughts move as you begin to fall asleep. You don't need to remember everything. You don't need to analyse or solve anything. Just listen. Let the words wrap around you like a blanket and picture the scenes in your own quiet way. To understand a supernova, we begin with something simple. A star, very much like the ones you see when you look up at the night sky. A star is not a tiny point in the sky. It only looks small because it is so far away. In reality, a star is a huge ball of hot gas, mainly hydrogen and helium, held together by its own gravity. Inside, at its core, the star is unimaginably hot and dense. Here, atoms are pushed so close together and so fast that they fuse. Hydrogen atoms merge to become helium. In that process, a tiny bit of mass is turned into energy. That energy moves outward from the centre, pushing against the weight of the star itself. The star is a delicate balance. Gravity pulling in, energy pushing out. When those two forces match, a star shines steadily, often for billions of years. So for most of its life, a star is calm. It is stable. It burns its fuel slowly, like a candle designed to last an age. But nothing in the universe is truly permanent. Eventually, the fuel begins to run low. And when that happens, especially in very massive stars, things start to change. When we talk about supernovas, we are often talking about the dramatic final moments in the lives of the most massive stars. Stars that are many times heavier than our own sun. These are stars that lived bright, hot and fast. They burn through their fuel quickly, living short and intense lives on the scale of millions, not billions, of years. When they come to the end, they do not fade quietly. They explode. But not all supernovas come from huge, hot stars. Some come from stars that are already dead in a sense. Small, compact remnants, called white dwarfs, slowly cooling in space. So, there are two main paths to a supernova. The first, a massive star that collapses under its own gravity. The second, a smaller compact star that suddenly gains too much material and becomes unstable. We'll visit both of these stories tonight. Slowly, gently, like walking through different rooms in the same ancient house. First, let's stay with a massive star. Picture a star that began its life perhaps 10 times, 20 times, even 100 times, more massive than our sun. From the beginning, it is brighter and hotter than the sun could ever be. Its light floods its surrounding space. Around it, there might be planets, gas, dust, perhaps even the beginnings of life somewhere, circling in the warmth. For millions of years, this star burns. In its core, hydrogen turns into helium. When the hydrogen runs out at the centre, the balance of forces is disturbed. Gravity begins to squeeze the core. The temperature rises. The star does not die yet. Instead, it changes. As the core heats, new reactions begin. Helium begins to fuse into heavier elements, carbon, oxygen. And as time passes, in a massive star, the core builds layer upon layer of different elements. You can imagine it like an onion with shells inside shells. In the outer layers, hydrogen still fuses into helium, Deeper in, helium fuses into carbon and oxygen. Deeper still, carbon fuses into heavier elements like neon, magnesium, and silicon. And at the very core, the star may eventually produce iron. Iron is important in this story because iron is where the star's power to create energy in its core reaches a kind of dead end. Up to iron, nuclear fusion releases energy. That energy pushes outward and helps support the star against its own gravity. But fusing iron does not give out energy. It takes energy away. So when enough iron builds up at the heart of the star, the core can no longer hold itself up with fusion. There is no new energy to push back. Gravity, which has been patient and steady for millions of years, finally wins. The collapse happens astonishingly fast. The iron core, maybe about the size of Earth, gives way in a fraction of a second. It's as if the floor beneath everything suddenly disappears. The core falls inward. The density climbs rapidly. Under such extreme pressure, protons and electrons in the core are crushed together to form neutrons. The core becomes like a giant atomic nucleus, a ball of neutrons. This new neutron-rich core is incredibly stiff. When the infalling material slams into it, the collapse rebounds. A shock wave is born, like a tremendous cosmic hammer blow, moving outward. At the same time, countless particles, called neutrinos, are released, carrying away huge amounts of energy. Some of that energy helps drive the shock forward. The outer layers of the star are blasted away in a titanic explosion. This is a core collapse supernova. The star, which may have shone steadily for millions of years, ends its life in a burst that can outshine an entire galaxy of billions of stars for a brief time. From far away, in another corner of the galaxy, the explosion might look like a new star appearing in the sky. In fact, that is where the word nova comes from. For people long ago, a sudden new star in the heavens was a marvel and a mystery. Nova, in Latin, a supernova, is simply a much more powerful version of that event. But up close, the violence is beyond anything we can truly imagine. Envelopes of stellar gas fly outward at thousands of kilometers per second. The shock wave rips through the star's outer layers, tearing them apart and hurling them into space. The light from the explosion races outward. As it reaches us, perhaps thousands or millions of years later, we see just a tiny, final flicker of a long ago catastrophe. For a few weeks or months, that light grows bright in our sky, and then it fades. What remains at the centre of that blast? Sometimes, the collapsed core becomes a neutron star. This is a city-sized ball of neutrons, only about 20 kilometres across, but with more mass than the Sun. It is so dense that a teaspoon of that material would weigh as much as a mountain. Sometimes, if the original star was massive enough, even the neutron star cannot survive. Gravity crushes it further. The core continues to collapse, down beyond anything we understand, forming a black hole. In both cases, a supernova has been born, and something new and strange has been left behind. Now let's leave that massive star for a moment and glide toward a different kind of ending. Far away, around another star, perhaps there is a smaller, sun-like star that has reached the end of its peaceful life. Such a star swells gently into a red giant. It sheds its outer layers slowly, forming a beautiful shell of gas. The core that remains becomes a white dwarf, a small, dense star, roughly the size of Earth, but with the mass of the Sun. A white dwarf no longer fuses elements in its core. It simply cools very slowly, glowing with leftover heat. On its own, a white dwarf may just fade quietly. But if that white dwarf has a close companion star, a different story may unfold. Imagine two stars orbiting one another. One is the white dwarf, small but dense. The other might be a normal star, still burning its fuel. If they are close enough, gas from the companion star can fall onto the white dwarf. The white dwarf begins to feed sip by sip, using gravity to steal matter from its neighbour. Over time, it grows more massive. There is a limit to how much mass a white dwarf can hold up against gravity. That limit is about 1.4 times the mass of our Sun. It is called the Chandrasekhar limit. If the white dwarf gets too close to that limit, it becomes unstable. Deep inside, as it grows denser and hotter, conditions change. Suddenly fusion can ignite again, but this time not in a controlled way. Not slowly, not gently. The carbon and oxygen in the white dwarf's interior begin to fuse in a runaway reaction. Within seconds, a thermonuclear flame sweeps through the star. The entire white dwarf is torn apart in a massive explosion. This is another kind of supernova, a thermonuclear supernova. In this kind of explosion, there is no core left behind. The white dwarf is completely disrupted, leaving nothing at the centre but a cloud of expanding debris. From far away it looks similar to other supernovas, a bright new point of light that shines intensely and slowly fades. But in detail, the light has a pattern, a fingerprint, that tells astronomers what kind of supernova they are seeing. The brightness of this type of supernova follows a fairly regular pattern. By comparing how bright they appear to how bright we know they should be, astronomers can measure their distance. In this way, supernovas have become tools for mapping the universe itself. They have even helped us discover that the expansion of the universe is speeding up, a sign of the mysterious force called dark energy. So, supernovas are not only the deaths of stars, they are also beacons that help us understand the cosmos. Now let's move back from the details and float in the bigger picture. Imagine once again that you are in that quiet field, looking up at the stars. Each point of light may have its own story. Some are newborns, just beginning to shine. Some are middle-aged, stable and calm. Some are elderly, red and swollen, near the end, and scattered across time and space. Some are about to explode, or have already exploded, long ago. A supernova might last only a few weeks or months in the sky, but its effects last far longer. The explosion sends heavy elements out into space. That is one of the most important things a supernova does. In the heart of massive stars, elements heavier than hydrogen and helium are created. Carbon, the backbone of life. Oxygen, which we breathe. Silicon, iron, and many others. Some of these elements are formed during the star's life. Others are forged in the heat of the explosion itself, in the wild storm of one last burst of nuclear reactions. Those elements are thrown outward into the thin gas between the stars. Over millions of years, they mix with that gas. They become part of new clouds, and those clouds eventually collapse to form new stars and new planets. You listening now are made of atoms that were once inside stars. Almost every element in your body, other than hydrogen, was forged in stellar furnaces, and some were created in supernovas. As the saying goes, we are literally made of star stuff. Supernovas are one of the main ways the universe recycles and enriches itself. Without them, the universe would be a much simpler, emptier place. No rocky planets, no metal, no complex chemistry, no life as we know it. If we could watch a supernova remnant, what's left behind after the explosion, over thousands of years, we would see it grow and spread. At first, not long after the explosion, the remnant is small, compact, and very hot. Gas rushes outward in a nearly spherical shell. It glows in many colours of light, including types our eyes cannot see. As centuries pass, the shell expands. It slams into the surrounding space, sweeping up gas and dust. The shape begins to twist and tangle, have played a surprising role in our understanding of the entire universe. When astronomers observed supernovas in very distant galaxies, they noticed something unexpected. Those supernovas appeared dimmer than they should have been, based on their distance. The simplest explanation was that the galaxies were farther away than expected. That meant the universe's expansion was not slowing down, as everyone had assumed. It was speeding up. Space itself was stretching faster and faster. To explain this, scientists proposed a new mysterious component of the universe: dark energy. We do not yet understand what dark energy is. We only know that it behaves as if it is pushing the universe richer in the ingredients needed for complexity, for planets, for life. Supernovas are both ends and beginnings. They are cosmic recycling events. The universe doesn't waste, it transforms. If you were to watch a single point in space for billions of years, you might see the full cycle. First, a cloud of gas, thin and cold, floating between the stars. Then a slight disturbance, perhaps the shock wave from a nearby supernova, compresses part of the cloud. Gravity grabs hold. The gas begins to collapse. As it collapses, it spins and flattens into a disk, with a growing star at its centre. Around that young star, planets formed from dust and rock and ice. The star ignites and shines. Life may arise on one of those worlds. Time passes. The star burns through its fuel. If it is massive, it ends in a supernova, blasting its enriched material back into space. The shock wave rushes outward. It collides with nearby clouds, compressing them. New stars form, new planets, new possibilities. The cycle continues. You're living in just one tiny moment of that great, slow, cosmic rhythm. Now imagine again that you are lying under that clear night sky. But this time, as you look up, you don't see the stars as fixed, eternal points. Instead, you see them as living things, each caught in a story that unfolds over millions or billions of years. Some are just beginning to glow, some are in their stable middle ages. Gravity grabs hold. The gas begins to collapse. As it collapses, it spins and flattens into a disk, with a growing star at its centre. Around that young star, planets form from dust and rock and ice. The star ignites and shines. Life may arise on one of those worlds. Time passes. The star burns through its fuel. If it is massive, it ends in a supernova, blasting its enriched material back into space. The shock wave rushes outward. It collides with nearby clouds, compressing them. New stars form, new planets, new possibilities. The cycle continues. You're living in just one tiny moment of that great, slow, cosmic rhythm. Now imagine again that you are lying under that clear night sky. But this time, as you look up, you don't see the stars as fixed, eternal points. Instead, you see them as living things, each caught in a story that unfolds over millions or billions of years. Some are just beginning to glow, Some are in their stable middle ages, some are quietly swelling at the end, and scattered across the galaxy. Some are in the split second between what they were and what they will become. A tiny fraction of their lives. A breath, an instant of collapse, a flash that races across the universe. A supernova. To you, the sky looks calm, but in truth, the galaxy is alive, with the slow, grand movements of birth and death. Supernovas are the fireworks of that long, gentle dance. If you could zoom your vision in on one single supernova remnant, say the Crab Nebula, you would see clouds and filaments of gas, each moving with its own speed and direction. Threads of glowing material twist and curl like smoke in slow motion. Some parts are rich in oxygen, others in sulfur, in nitrogen, in iron. If you wait thousands of years, those filaments drift farther apart. Eventually, they will mix with the interstellar medium, the thin sea of gas that fills the spaces between stars. There, tiny grains of dust may form. On those grains, atoms may stick. Simple molecules may arise. Hydrogen and oxygen may combine into water. Carbon atoms may join into complex chains. Chemical richness grows. These are the tiny steps that, much later, make chemistry like the chemistry of life possible. And long after the original star is forgotten, its scattered pieces will be part of something new. Astronomers use many kinds of light to study supernovas and their remnants. Our eyes see only a narrow band of colours, but the universe radiates across a wide spectrum. Radio waves, microwaves, infrared light, visible light, ultraviolet, X-rays, gamma rays. A fresh supernova remnant often glows brightly in X-rays, where very hot gas shines. Older remnants may appear brighter in radio waves, as charged particles spiral around magnetic fields. By combining all these different views, astronomers build a more complete picture of what happened. It is like listening, not just to one instrument, but to an entire orchestra playing together. Each part gives us different information, and together they form a more complete song. Sometimes supernovas are not perfectly symmetrical. The explosion can be lopsided, sending more material in one direction than another. Jets and blobs of gas are shot out at different speeds. We do not yet fully understand all the details of why this happens. Explosion is complex and still being studied, but these irregularities can give the remnant a twisted, asymmetrical shape. They can also kick the neutron star left behind, sending it flying through space at hundreds of kilometers per second. These runaway neutron stars are like cannonballs shot from the dying star, racing across the galaxy. Even in death, the star sends out fragments with their own paths and destinies. In more recent years, astronomers have not only seen the light from supernovas, they have begun to feel their ripples in a different way. When extremely massive stars collapse to form black holes, or when neutron stars collide, they can send out waves in the fabric of space itself. Gravitational waves. These are tiny stretches and squeezes of space, passing through everything, including you and the Earth. They are so faint that they are incredibly hard to detect. But we've now built instruments sensitive enough to feel some of these ripples. Although most of the gravitational waves we have detected so far come from merging black holes and neutron stars, not from ordinary supernovas. The idea is the same. Violent events in space shake the universe. Those shakes travel outward as waves. Supernovas are a part of that story. When we eventually learn to hear their gravitational waves more clearly. We will have yet another way to listen to the deaths of stars. For now, as you lie here in your imagination, letting these images drift through your mind, think about timescales. A human life might last 80 or 90 years. A tree might live a few hundred years. A civilization could last thousands, maybe tens of thousands. A star like our sun lives about 10 billion years. Massive stars live shorter lives, but still tens of millions of years. A supernova explosion, in contrast, is incredibly brief. The actual collapse and explosion might only take a few seconds. The bright phase, when we can see it clearly in distant galaxies, lasts weeks or months. The remnant lingers for tens of thousands of years. Then it fades and blends into the background. In the grand story of a galaxy, a supernova is a sudden shout in an otherwise slow, steady song. Yet that shout changes everything around it. It stirs the gas. It creates new elements. It seeds the birth of new stars. But the material it cast off remains, drifting outward, spreading, mixing, becoming part of something larger. The spark is gone, but its influence continues. Supernovas are like that. And in a way, so are we. We live. We shine in our own small ways. We change the world around us, even if only a little. Then we fade. But we are made of matter that will go on. We are part of a chain that began in the hearts of stars. And somewhere, out there in the darkness, even now, another star is quietly reaching the end of its life. Another supernova is preparing to bloom. Its light will travel across the universe, across ages to reach some distant shore. Perhaps on some world, someone will look up, see that brief new star, and feel a quiet sense of wonder. The universe will go on, slow and vast and deep. Stars will live and die. Supernovas will come and go. Your mind has begun to wander as you listen. That is all right. Let it. You might find yourself picturing a single star, alone in the darkness, bright and steady. You might see it swelling into a red giant, its outer layers puffing out. You might imagine its core collapsing, the rush inward, the sudden rebounding shock. You might imagine the flash of the supernova, its light racing outward. Then imagine that light travelling across empty space for thousands or millions of years until it reaches a distant world where a being like you looks up and sees a new star in the sky. For that observer, in that moment, it is simply a point of light, a wonder, perhaps a mystery. For the universe, it is one more step in a long chain of transformation. Birth, life, death, and then from the ashes, new beginnings. Some cultures, long ago, saw supernovas and recorded them as omens. A sudden star might mean the birth or death of a king, a sign from the gods. They did not know the physics. They could not measure the spectra or calculate the energy output. But they felt instinctively that something powerful had happened. In a sense, they were right. Our modern understanding gives different meanings, but the all remains. Even now, when a new supernova is discovered in a distant galaxy, astronomers all over the world turn their instruments toward it. They measure, they study, they try to catch the earliest moments. They try to piece together the star's life before it died. And through it all, the same atoms will keep moving, joining and separating, telling the silent story of everything that has ever been. Thanks for joining us today. I hope you found today's story soothing and interesting. If you'd like to join us for future sleep stories, subscribe to this channel. If you would like to request a story on a particular topic, drop it in the comments and I'll do my best to cover it next. Good night, sleep well.